Hello everyone, this is Jose with Risk Management Professionals, and in today's webinar, we are going to be talking about knowing when and which safeguards to credit. So I have noticed during PHA sessions that there is a lot of confusion in the team when it comes to why or why not we can credit certain safeguards. So in today's presentation, I'm going to elaborate on what makes a safeguard credible in a PHA. So just to give a little background about risk management professionals, here's an overview of the services we provide to our clients. If you would like more information or would like to see some more examples on the services we provide to our clients, you can always check out our website at rmpcorp.com. Once again, that is rmpcorp.com. So let's start off with the types of safeguards. So this is not a complete list of the safeguards that can be credited during a PHA, but these are certainly a list of the most common types of safeguards you will see during a PHA. So starting off with alarms, these would usually be the safeguards that you see the most during the PHA, as they are commonly used in all industries such as oil and gas, ammonia refrigeration, etc., etc. So you might see a low flow alarm on the discharge of your pumps to alert your operators to prevent a cavitation or deadhead scenario on your pumps. Moving on to interlocks, you might also see a low pressure switch that trips your furnace off by closing your fuel gas supply valve to prevent flame out in your firebox. Pressure relief valves are commonly used on vessels where there are overpressure concerns. If your vessel begins to overpressure, your pressure relief valve will hopefully go open and prevent any catastrophic rupture of your vessel. Administrative controls are a bit more generic, but these would involve any operating procedures or operator rounds for your specific scenarios or specific hazards. Alarms. So alarms will probably be the main safeguards you see during the PHA. Whether it be a low flow or low level alarm, these are commonly used in every industry. You want to avoid crediting too many alarms for the same scenario. There's no real reason to have 10 alarms credited for the same scenario, even though you may actually have 10 alarms for that specific scenario. The best practice is to credit the alarms that you will see first or that your operators will be able to respond to first. It is also important to only credit alarms that your operators will have enough time to respond to. Best practice is to credit alarms in which your field operators will have 20 minutes or more to respond to the alarm. And for your board operators, you will want 10 or more minutes for them to be able to respond to that alarm in time so that the issue can be fixed from the board. Interlocks. So these interlocks are automatic systems that will close/open valves and override your system depending on the hazard. You want to avoid crediting interlocks that are tied into the failure point. If your flow control valve failed close, you don't want to rely on the transmitter tied into that valve to swing that valve open, as the cause of failure may be due to that transmitter misreading. The main thing is to make sure that the interlock is reliable. You do not want to end up in a scenario where your operators believe something will trip and then it does not trip. This could end with an injury or possibly worse to your personnel. Moving on to pressure safety valves. Pressure safety valves protect the process and people from overpressurization. These valves will fly open upon reaching the set point pressure. It is important to make sure that your PSVs are sized appropriately. You do not want to end up in a scenario where the PSV does not work because it was not sized accordingly. This could create a false sense of security for your operators and make them feel protected when really they're not, and this could result in a major injury. Another thing to note is to conduct proper inspections regularly and that the PSVs are maintained accordingly so that these PSVs can be credited in a PHA confidently. You always want to make sure that your PSVs route to a safe location, for example, a flare system or even to an elevated location away from any personnel. Moving on to administrative controls. These are generic safeguards which should typically be avoided. However, operator rounds are generally assumed to be available for all scenarios. Operator rounds can be credited so long as they are detailed towards a specific scenario. For example, tube inspections are conducted every turnaround to check for any potential tube leaks. These Another example may be operator rounds that include testing for contamination for that specific process. So let's say you had a tube leak into your cooling water tower. Maybe you would want to check for hydrocarbons in your cooling water to prevent any possible fire hazards. Another point in this presentation is to find ways to avoid wasting time during a PHA session. Firstly, operational impacts do not require safeguards to be credited. If it is just an operational impact, you do not even want to spend minutes discussing the scenario so long as the team it is sure it will not result in a safety or environmental impact. As soon as the team identifies a scenario as an operational impact, the facilitator and the scribe should note it down on the worksheets and move on to the next scenario. The focus should always be on safety and environmental impacts mainly. Now, let us start looking at actual scenarios we may see pop up during the PHA. In this instance, we'll be taking a look at a control loop failure versus a manual valve failure, and we'll be taking a look at the differences in the safeguards that can be credited. So here we'll be taking a look at a pump failure scenario. We're going to focus on three specific scenarios: the manual valve on suction to the pump shown on the leftmost red arrow, the manual valve on the discharge of the pump, and the flow control valve on the discharge of the pump shown by the red arrow at the top of the slide. For these scenarios, we are going to assume that the manual valves inadvertently close, and we are going to assume that the flow control valve failed close due to the flow transmitter misreading, which can be seen on the right side of this slide. We are also going to assume that the flammable hydrocarbons are flowing through this pump. So how would these scenarios look written on a PHA worksheet? In an actual PHA, the PHA worksheets should be a little more detailed than this in that they should contain P&IDs, equipment names, and equipment tags, but this will at least give us a good idea as to what the scenario might look like. So firstly, we're going to focus on the manual valve on a suction to the pump inadvertently close. So that is cause 1.1.1 on the worksheet there. If the manual valve inadvertently closed, then the scenario we would see with no safeguards is a potential loss of suction to pump leading to cavitation, seal failure, and release of flammable material. This will lead to a potential flash fire resulting in a personnel injury. So in this theoretical scenario, we're going to say that the team ranked this as a B, which would be a permanent disabling injury to personnel. Now for our safeguards. For this scenario, one of our safeguards might be dual seal alarms, which are configured to alert operations upon failure of the primary seal for the pump. And our second safeguard is that our flow transmitter is configured to alert operations upon low flow from the pump. So with these safeguards, the team ranked the likelihood of this scenario to be a 4, which would be highly unlikely. If we take a look at our risk matrix down below, we will see that a severity of a B and a likelihood of 4 would give a risk ranking of 4, which can be seen in blue there. This would mean that we are safe currently as is. Now let's take a look at cause 1.1.2, where the manual valve on the discharge of the pump inadvertently closed. We will see that the scenario is the exact same, other than now we are blocking the discharge of the pump and we are deadheading our pump rather than cavitating it. But the risk ranking remains the exact same. So let's move on to the next scenario, which will be cause 1.1.3, where the flow control valve malfunction closed on the discharge of the pump. So as we can see, the consequence remains the exact same, but now we cannot credit our flow transmitter safeguard as this is the cause of failure. We cannot rely on this alarm to protect us as it may not be functioning as intended when we need it most. So as we can see, the team felt that without the safeguard, the likelihood of this happening went up to a 3, so they felt it was slightly more likely to happen. So the overall risk ranking also went up to a 3 because of this. Now, this does not necessarily mean that without the safeguard, the likelihood of the scenario has to go up. If the team feels that with just the dual seal alarms, they feel safe enough to rank this with a likelihood of 4, that is entirely credible to do so, so long as the rest of the team agrees. At the end of the day, it is up to the team to decide on whether or not they feel safe. That is why it is important to have PHAs to gather everyone's opinions and find gaps in their process. So next, we will take a look at an overpressure scenario due to external fire. So as we can see from the image, the design pressure of the vessel is 100 psig. For PHAs, we always have to assume the worst possible scenario. So in this instance, we will assume that the vessel pressures up until it reaches 3.5 times MAWP. In other words, the pressure of this vessel which will reach 350 psig for this scenario. So now let us take a look at the safeguards we can credit from the scenario by first taking a look at the cause, which would be external fire near gas vessel. So the consequence for this scenario would be potential for flame impingement and overpressure up to 3.5 times MAWP of your gas vessel. This would lead to a potential fire resulting in personnel fatality with a severity of A, which would indicate a fatality. So for safeguards, we credited our PSV 104, which is designed to relieve to the flare system and is sized for external fire for your gas vessel. The team ranked this as a likelihood of 4 and overall a risk ranking of 3. What do we want to take away from this scenario? When crediting PSVs, we always want to make sure that your PSV is properly sized for that specific scenario, which in our case would be an external fire. So by the time the PHA is in session, hopefully calculations should have been done to verify that the PSV is sized for each specific scenario. If the PSV was not sized for external fire, then maybe a recommendation may have to be made to upgrade / replace the PSV if need be. A PSV not being sized for each specific scenario does not always result in a recommendation to replace the PSV. We will talk about some of these exceptions in the next slide. So now we're going to talk about vessel overpressure due to blocked outlet. We'll be taking a look at HV 105 on the outlet of the gas vessel inadvertently closing in this scenario. So the design pressure will be assumed to be 100 psig as it was in the last scenario. So once again, we'll be taking a look at how the scenario would look like on an actual PHA worksheet. So I have copied over the external fire scenario to compare the differences between a blocked outlet scenario and an external fire scenario. So first, let's take a look at cause 1.1.5, in which HCV 105 manual valve inadvertently closed. So the consequence for this would be potential block vapor outlet leading to overpressure of your gas vessel up to 2.0 times MAWP. So this will lead to a potential flange leak and a potential release of flammable material, which can then lead to a potential flash fire resulting in a personal fatality, which would mean this would be risk ranked as an A. So next we would take a look at our safeguards credited, which in this instance, it was PSV 104, which is designed to relieve to the flare system and is sized for external fire for gas vessel. However, the relief capacity was sufficiently oversized for this case, and thus the team considered the relief capacity to be sufficient for a blocked vapor outlet scenario for the gas vessel. This resulted in a likelihood of 4 and overall a risk ranking of 3. So why were we able to credit PSV 104 even though it was not sized for a blocked outlet scenario? So the reason is, in the external fire scenario, pressure reached up to 350 psig, whereas in the blocked vapor outlet scenario, pressure only reached up to 200 psig. So the team felt comfortable crediting PSV 104. I would usually still try to push a team to make a recommendation to verify that the calculations from PSV 104 prove that it can protect the vessel from a blocked outlet scenario. However, it may not be necessary if the team feels safe without the recommendation. It is good that you can credit the PSV in this instance, but this is not always the case. So in a liquid overfill scenario, we may pressure up as well above MAWP, but that scenario may react differently than an external fire scenario, and therefore the PSV may not be credited. It is always best practice to make sure that your PSV is sized for each specific scenario, whether it be a blocked outlet, liquid overfill, or external fire. calculations should be made for each consequence. We appreciate everyone taking time out of the day to watch this webinar. For more information, you can contact me below or find more resources, services, and webinars at rmpcorp.com. Thank you once again.